Hey, my name is Aleksander Madry, and what I want to do today is to tell you a little bit about adversarial robustness and what we learn in studying the subject and how this relates to computer vision. So let's get started. And I just want to acknowledge my great collaborators, most of them, but not all of them, my students, who contributed to this work and made this possible. So, right. So the point of start here is this realization that will not be new to you, is that machine learning is truly a success story. Indeed, you can say that things started with the ImageNet progress, but since then, we seem to be able to do so much more. And essentially we are thinking of using machine learning in all the different aspects, and in particular, in the context of different applications of computer vision. So this is all great, but kind of the point for start for me, at least in this context, is the realization that as amazing as these developments are, they are still a little bit lacking. And in particular, machine learning can still be quite unreliable. Okay, so just to give you an example, so what you hear over here is the relatively old demo of Tesla car, and it's great. It's really like at that time when it came out, it really looked like science fiction. So this is all great, but even though this demo was 2017 or maybe even earlier, this is a video from just last year that shows a Tesla car, which there's an overturned truck on the highway, and the Tesla just drives right into it on the autopilot mode. That shows that, well, things are not perfect yet, and sometimes the computer vision in particular that drives these cars can fail. Okay, so this is kind of the motivation. And what I want to do today is I want to kind of attempt to put this unreliability in a broader context, and in particular, connect it to some of the computer vision concepts and applications that you might be interested in. Okay, so let's do that. And I think a good point of start for that discussion is to actually try to stop for a moment and ask ourselves, okay, so why do we like deep learning? And of course, like deep learning for one thing is that it seems to really work. So we just kind of take this high dimensional input like, images, we put it into our model, we train it. And what we get out of that is this very nice learned embedding of these images that essentially allows us to apply a linear classifier to make sure, to make pretty good classification. So that's kind of, one answer to that question. But I would say, at least to me, what I really like about deep learning is not only that it just solves these tasks, but the way it solves it. In particular, the fact that, essentially as a byproduct of training a deep learning model, you are getting this hierarchical structure, these representations that you can actually take a look at and utilize. So we all know this kind of, I would say hypothesis, or actually something that seems to be more or less true, that different layers of the neural network correspond to different representations, and these representations become kind of more high level. So maybe the initial levels correspond to recognizing some edges or shapes, but as you go deeper and deeper into the network, kind of you get more and more and high level concepts. So that's one reason why having this very nice way of representing the data is kind of extremely useful, and we can do a lot of really cool stuff with it. And essentially, like at least one of the other cool ways of applying deep learning is to create all these great generative models and kind of leverage these representations or learn them in a bit different way. And then you can do all this amazing way of creating objects that do not exist and get a lot of photorealistic kind of artifacts that kind of, again, were learned in a purely data-driven way. Okay, so this is all great. This is why we all like deep learning, but, well, there is a but here. Okay, so as much as deep learning was the technology of choice, it does not work as reliably as we would like to. So, okay, here is another just Tesla malfunction, but then we have plenty of examples of just images that get misclassified, even though clearly they should be classified correctly. And in general, even if we look at this representation, we realize that kind of things are not exactly as they should be. So in particular, one thing we notice, and I'm sure we're not the only one to notice, is that it's actually, even if you look at this final layer or penultimate layer representation, it's not too hard to find two images that essentially seem to be very close in that representation, but are actually completely different to us visually. Okay, so clearly this representation is not kind of capturing what you would really like it to capture, namely our visual perception and the notion of what makes two images visually similar. Okay, so that's what we observe if we dig a bit more. And then the question is like, well, what's going on? Like, why are these glitches and problems happening? And I would say that the problem that is kind of at the center of all of that is this question of adversarial examples. Okay, so by now we all know what adversarial examples are. Here is just one of these examples. And as you know, like a lot of effort over the last 3 to 4 years was to figuring out, how to get models that are robust to this kind of adversarial examples. Essentially, we would like to get adversarial robust generalization in which we would like to get a model whose performance is good, even if we measure it in not just by expected performance on a random image from a test set, but actually we look at the worst case perturbation of that random test examples, and we want to kind of optimize that. So again, so this is the goal, and I would say we are finally, it took a little bit, but we are finally starting to succeed here. Again, we are very far from being done, but I think we made some real progress here. And that's, I could now give a 1 hour or even longer talk about all the cool developments that happened there. But of course, that's not the goal for today. What I would like to kind of tell you about today is, okay, so if you look at all of this body of work that was done around adversarial robustness and it was kind of inspired by adversarial robustness, the question is, okay, so what would I take away if I actually didn't care about adversariality of adversarial robustness? Essentially, if I didn't care about adversaries, all I just wanted to do is have better vision models. Like, what kind of takeaways should I get from that? Well, I would say that first of all, even if you don't care about adversarial examples as a realistic threat to your system that you are deploying, I would view them that they're not only a problem that, again, if you are more security minded, you might worry about, but they're also a symptom of some deeper problem. So in particular, I already said that, in some ways, what really adversarial examples tell us is exactly about this brittleness of the representations, that there are images that, well, on one hand, are visually very different to us, but might be close in their representation, and complementary, that there are, images that are, very similar to us, but turn out to be quite far in this embedding that the model finds. So there is a certain misalignment of representation with visual perception. Also, the other thing to think about is that, again, instead of thinking of, okay, we are trying to, kind of avoid some kind of brittleness, oversensitivity to adversarial examples, what we really might think about when we talk about robustness to adversarial examples, that we are trying to impose some invariance. So essentially, if you, again, look at the goal of what we are trying to accomplish, when we are talking about adversarial robust generalization, you might think of this kind of set of allowed perturbations as some kind of desired set of invariances. Because if you think about that, that's what you really are telling, is that you are saying, okay, I want your performance to be robust, invariant, under this set of transformations. Okay, and again, there is no longer need for an adversary. This is just a way of regularizing the model. And finally, the kind of, I would say, even the most important, at least to me, realization is that in the end, it is all about features that our models use to succeed. And in particular, there is this emergent realization that essentially what we, the more I work on adversarial robustness, the more I look into this, the problems that emerge from there, the more I realize that it all goes back to something very simple, to this realization that just the fact that our model succeeds at a given task we put in front of it, let's say, getting very good, ImageNet accuracy, test set accuracy, does not mean it's actually learning the thing that we believe, one needs to learn to succeed at that task. So in other words, imagine I want to train my model to recognize dogs versus cats or versus other classes of images, and kind of my, the way I as a human like solve it is I by just look at, at things like snout, at the shape of the ear, the four eyes, all of that. This is how I as a human recognize that the dog is a dog, and that's fine. But somehow also that's what I implicitly assume that the model has to learn, these concepts of a snout and an ear, to succeed at this task as well. However, this turns out to be not the case. And actually, there turns out to be completely different ways of solving the task of, of differentiating between cats and dogs and other classes of images that essentially like, yeah, does it completely differently to how we human would do it, or even would be able to do it. And there is a priori no reason for our models to favor the human version of solving the task, because it just tries to get the job that you actually put in front of it done. And in the end, this kind of misalignment, if you dig a little bit deeper into literature, you will quickly realize that, yeah, that this is kind of something that we are discovering over and over and over, where whenever we have kind of this result where we see, oh, for instance, the models seem to depend much more on the texture than the shape, compared to a human. And there are they are using, higher frequency Fourier features than human would, and so on and so on. This is just a projection of this kind of broader realization. And essentially, like when we in our group were trying to make sense of it, it's kind of the conceptual models that we kind of that emerge of this thinking is something that we call now the robust features model. So what is the robust feature model? Well, the robust feature model kind of tries to provide us with some way of thinking of like how should we classify different features that our models might be using for solving the task we put in front of them, in particular classification task. And somehow, if you think about this task, if you just like think about like how could I classify all the features that my model might use, you might start about trying to just partition these features into useless features and useful features. So essentially, useless features are something that are completely not really correlated with the task of interest to us. They are they don't have the correlation with the label we actually care about. They are completely useless. They're just spurious, some kind of spurious patterns. And then there are everything else, which is the useful features. So features that actually kind of provide us with information, correspond to patterns that really provide us with information that enables us to solve the classification task. And somehow in particular, where people were thinking about adversarial examples, the hypothesis was that they really correspond to that our models for some reason kind of develop sensitivity to useless features, even if they are not useful for classification tasks. And adversarial examples are just manipulating these to sway the decisions in the wrong way. So that was kind of the point of start for our robust features model. But then when we looked deeper into it, we realized that this picture is a bit oversimplistic. And in particular, one really needs to dive deeper into what useful features are. And when you do that, you will kind of realize that there is, a bit more fine-grained classification of features, that essentially the one that we call robust features. So these are features that are indeed correlated with the label that we are trying to predict, and they remain to be correlated even if we try to perturb them in a variety of ways. So these are what robust features are, and in particular, everything that a human would use to solve classification task would fall into that category. So that's what robust features are. But then what we discovered, and this was like a huge surprise to us, is that actually there are also other types of features. We call them non-robust features. So these are features that are also correlated with the label. So they're also useful, but actually they are fragile. Essentially, they can be flipped via perturbation that essentially would be imperceptible to humans. So now there are these two types of useful features. And actually what we also are able to show is that when you think about adversarial examples and you try to understand why they are so successful and so widespread, well, the reason is that they really correspond not to manipulating the useless features, but actually these non-robust features. Okay, in particular, what is happening here is that, well, the only thing our models try to do is to maximize this accuracy. So they're willing to use whatever features will be useful to achieve this task. And it turns out that non-robust features have a ton of very useful signal if you just care about predicting well on the test set. So as a result, models use non-robust features a lot. And this, unfortunately, well, this makes them work great in terms of test set accuracy. But unfortunately, this also what exposes them to kind of this oversensitivity to the adversarial perturbation and makes them non-robust. Okay, so that's kind of the realization that you should really try to think about the models that your model uses kind of by classifying them into these two categories. And now, once you do that, there's a lot of new perspectives on all the different functionalities and kind of questions and phenomena that we observe when we try to make sense of how our current machine learning model works. So particular, there is this view also provides a new perspective on interpretability. So essentially the goal of trying to be able to understand and kind of scrutinize, why a model made the decision that it made. And kind of the new perspective corresponds to the realization that, well, if if my model might rely on robust or non-robust features to make its decisions, and actually it tends to depend on non-robust features, disproportionately much, then, well, the problem with non-robust features is that even if they are useful for getting good test accuracy, they actually might not make no sense to human. And it might happen that yes, the model is driven by these non-robust features, but there is no hope for us humans make sense what these features are and in what way exactly they inform the model's prediction. So now, if you try to think of interpretability as this kind of post hoc task in which I just give you my model that I train, and you are supposed to explain to me what this model does, well, then you are in trouble, because either you will tell me what really drives my model prediction by kind of exposing the non-robust features, but I will have no idea what it means, so it will be not really useful to me, or you will just maybe kind of just constrain the explanation, just project the explanation on the space of things I can understand. But then you will be essentially suppressing some of the important drivers of model behavior. So essentially, this will not be really a truthful interpretability method. So in particular, one learning from that is that if you really want to get interpretability, you can't think of this as just a post hoc task. You need to essentially plan for this already at the training time to make sure that even the features that drive your model's prediction mechanism are something you are in principle able to understand. Of course, no, how to surface these features will still be a challenge, but at least you have a hope and chance of succeeding. Okay, so that's one new perspective on interpretability. But also, it kind of is really a great lens, like this robust features perspective. It's a really great lens at understanding, okay, what are kind of the approaches that already we know are successful in the context of adversarial robustness, why they are successful. So again, if you go back to this model and you think about this, trying to get this goal of adversarial robustness, in particular, like, now you can think of like, adversarial robustness as a prior, as kind of, I try to imbue my model with this regularization corresponding to being adversarially robust, to this corresponding to its invariances. Then if you think about what this objective is doing, it's really kind of trying to make sure that the prediction of your model is not dependent on non-robust features. Essentially, like what this kind of max over this invariances tells you is that, well, whenever you will be really depending on non-robust features, kind of this max will punish you for that by finding a perturbation of these features that essentially flips them, that makes your prediction incorrect. So essentially, to perform well according to this metric, you really need to not like steer away from non-robust features and make your decision be driven by robust features. Okay, so that kind of is one way to explain why adversarial robustness, like what effect it has, and why, what does this prior correspond to? And essentially, if you start thinking about that, so essentially, if you realize that, okay, making a model adversarially robust makes it depend more on robust features versus non-robust features. So you think of this about this prior, you might ask about, okay, so what implication this might have to making models be actually better. So forget about adversaries, about being robust. Like if I just think about this adversarial robustness as just a prior, to what extent will it impact the model? And in particular, this is a question we ask ourselves in a series of papers. Essentially, we try to understand, how do adversarially robust representations in particular look like? Okay, so again, putting the security hat aside, just like, how do they look like? Are they maybe better in some sense than the standardly trained models? Well, without spoiling too much, the answer is yes, they actually tend to be better. And let me illustrate in what ways. So the first thing that we observe is actually like this robustness prior implies more like better perception alignment. So here's just like one simple way of visualizing this. So as you know, one way of trying to intuit, what drives models prediction is to essentially look at the pixel influence heat map. Okay, so what I do is I look at every pixel of an image and I check how much perturbing this pixel can influence the prediction of the model. And this way, I guess such a heat map. And if I apply this heat map to a standard model, I will get things like that. It kind of makes sense. It clearly is sensitive at the places that it should be sensitive, but also it's sensitive at places that maybe it shouldn't. Right? There are just some elements of the background that it still seems to be, be sensitive to. And that's so you might say, okay, that's good, but maybe not perfect. However, what we observe, if you apply the same vanilla technique, but to a model that is already trained to be robust to the small pixel-wise perturbations, you are getting, heat maps like that, just right out the box. And clearly this is much more aligned to what you as a human would expect is the correct heat map. So this is just a simple example, simple intuition, but kind of this goes further. So what we essentially observe is that if you go back to this representation level view, then essentially again, if you look at this second to last layer representation of a model, in standard models, it's very easy to find images that are completely different, but essentially correspond to the same representation. However, if you look at robust models, well, we were not able to succeed in finding two different, visually different images that actually give you the same representation. So there seems to be, again, this overall kind of alignment, by making a model robust, you align the representation much more tightly with what is perceptually, perceptual distance to us humans. And again, in some sense, this makes sense because robustness is really about providing this invariance to pixel-wise, small pixel-wise perturbations, which is again, human visual representation is also robust to that. So essentially, by putting these constraints, you are clearly aligning the way a given task has to be solved with the way humans would solve. It doesn't mean that it will be identical, but it turns out that even simple robustness criteria already push us quite a long way. Okay, and indeed, you can dive deeper. You can look at direct feature visualizations, and again, you are getting things that are much closer to what we as humans can make sense of. You can kind of identify features that really correspond to concepts you can name. So you can essentially realize how to add stripes to an image by just kind of identifying a neuron that corresponds to them and kind of that just exciting it appropriately. You can get this kind of semantic interpolations, which essentially you can get in a very simple way where you just look at the latent space, representation space between two images. You look at the, a geodesic, just the straight line in the representation space, and then kind of look at the images around this line, whose representations are around this line, and you are getting this kind of, interpolations right off the box. And then you can go even deeper. You can kind of try to essentially leverage this representation that you are learned to create generative models. And again, this clearly is nothing close to the generative model that we currently have, but essentially this is just something you can get just with a few lines of code and really not trying hard, really doing extremely simplistic things. And this actually looks reasonable, or at least would look reasonable around 2017. So just yes, we are definitely moved a long way from there in terms of generative models, but that was paid with a huge engineering price. And here there was the engineering price was essentially zero. It was just a half an hour with the code, and that's already where you get, just because the quality of representation is so good. So you can do also things like image translation. You can do super resolution, you can go in painting. And again, this will not be state of the art right now, but again, these are things that you can get in an extremely simple way. Okay, so clearly the representations seem to be, once they have this robustness power, they seem to be better. But now the question is okay, how would you use it exactly? Okay, so, one particular capability that we in our group pay a lot of attention to is kind of what we call counterfactual analysis. And this is a counterfactual in quotes because we don't really have, this is not a counterfactual analysis in this kind of precise causal inference sense, but you will get the idea why we use this name. So essentially, just to explain you what we are after, here's an example. So this is the image that I showed you at the beginning of the talk of an example of an image that, well, the model gets wrong. So this is an ImageNet, as an ImageNet picture, and an ImageNet model gets it right, gets it wrong, sorry. And even the robust model, a robust ImageNet model also gets it wrong. Okay, so the correct label is insects here, but for some reason the model claims this is a dog. And you may say, okay, that's not the only image in the world that our models will get wrong. Let's just move on. But actually with robust models, it's not hard to ask a question of, okay, if you believe that this is an image of a dog, can you enhance kind of the dogginess of this image to show me essentially what would make you convince even more that this image is a dog? And when you do that, you will get the image eventually on the right. And if you look at the top left corner, well, there is clearly a dog there. That's not surprising that this is viewed as a dog. But if you look at the original image and the top left corner, and you will squint your eyes, you realize that there also it looks like a dog's head. And since ImageNet has so many dogs, the whole model is biased to, whenever it can see a dog, it will predict dog. And that kind of explains to you, what really drives this wrong prediction on this particular image. And actually, like, you can say, okay, in retrospect, this actually completely makes sense. And you can, take some action to try to fix that. So this is just a simple example of what we call this counterfactual analysis, but this can be pushed further. And actually, in recent work, we actually indeed try to do that, and kind of we push these developments to try to build something that we call like more debuggable deep networks. Okay, so what is the idea here? So the basic idea is just to look at what I would call the anatomy of deep neural network, in which kind of we view it essentially as consisting of two parts of this like deep representation, like feature representation, that just takes the input and essentially encodes it into this ultimate layer representation. And then there is this linear model that essentially, based on this representation, makes the final decisions. Okay, and so in some ways we can view like this, first part that's corresponding to what the network learns, and essentially the last part, the linear model, is how the network makes decisions based on kind of the digestion and kind of understanding of the data that it ingested. Okay, so these are the two parts. And now what we would like to do, well, we would like on the one hand make this kind of this feature extractor be more interpretable. And on the other hand, we would like this kind of decision layer to be more sparse. So actually we have even a hope of trying to understand it. So this is kind of the desiderata, and like, how do we execute it? Well, to find the more interpretable deep representations, well, it's kind of something that the field was working for quite a while. So you can reuse much of existing interpretability tools. So you can kind of, look at, different ways in which people attempted to kind of make sense out of the feature that, that the model learns and extracts from the data. In particular, again, we actually, for vision models, like we also apply it to NLP languages, but for vision models, we also use, robust models to get this kind of more perceptually aligned representations. But that's kind of how we get, implement this, the first step of this more debuggable deep neural networks. But then for the step two, we again want to find a sparse linear layer. And of course, you might just say that, okay, so to find sparse linear layer, I just take a network and I just figure out some sparsification procedure to do that. But when you do that, you realize that actually it's really difficult to sparsify the network to any reasonable degree without degrading the performance of the network by a lot. So what we do instead is actually we retrain this linear classifier on this linear representation, and we kind of just regularize this, doing this retraining this linear layer to make sure that it's actually sparse. In particular, we use something called elastic net regularization, which on one hand kind of makes sure that kind of the network makes right decisions, but on the other hand penalizes it in a way that enforces that like the connections between the particular features and the decisions are as sparse as possible. Okay, so that's basically what the setup is. And now the question is like, no, it's relatively simple. How well does it work? Well, a spoiler alert, it works pretty well. So first of all, let's look at the ImageNet. And by the way, to implement this for ImageNet, you really have to do a little bit of heavy lifting because, just to make sure things are scalable, but we did that and actually we released the call. And essentially now the question will be, okay, so as I'm trying to sparsify, so to keep my, my linear layer to be as sparse as possible, like how much do I need to pay in performance for that? And the answer is that actually not much. Essentially, that actually this was quite surprising to us that you can get significant sparsity without paying much in the actual test performance. And in particular, if you look at the restricted ImageNet, which is essentially 9 kind of big balanced classes of ImageNet, what you can get is essentially you can get like really, really good performance. Essentially, you can get 5% loss in accuracy while retaining only 1% of connections that you actually get. So there is a huge kind of, there's a huge opportunity here that you can get a lot of sparsity by just, sacrificing relatively, not significant amount of accuracy. And, once you do that, you actually can look at these features and you can start trying to make sense of them. And in particular, then you realize that, okay, as this, there was this kind of, a hypothesis / belief that, different layers correspond to more and more high level high-level representations. And indeed, that's what we seem to be finding when we kind of analyze what's happening. And of course, like we are very focused on trying to use this, these models for, for something that, that connects to robustness. So we kind of find the way to use this tool to diagnose undesirable correlation. So essentially, you can look at, at different features. You can try to figure out like which classes in the dataset use it, what actually these features seem to be activated on, and based on that, understand kind of what potential problems might emerge in your model. And then you can kind of go further and you can try to pinpoint misclassification. So you can look at at an image that was mispredicted, and you can try to understand why which features caused misprediction and why. And essentially, it's very easy to kind of, have the discussion about the failure of the model in a particular example, be quickly reduced to a, manageable, like, a cognitively manageable discussion of just like, looking at, some small number of features and understanding like what really happened here and why. Okay. So this is kind of the, one of the functionality that we care about quite a lot. But of course, again, we really care, and that's where the counterfactual comes from, is that like, the interventions we make and the kind of correlations and, and potential, problems that we find, they really correspond to real things. In particular, they are causal. And for that, we kind of used, a lot of, well, first of all, we wanted this predictions to be causal, but also we wanted, when we talk about, ability of humans to diagnose what the problem is, well, we really wanted to make sure that this is indeed the case. So it's not just us hallucinating and having some confirmation bias that, oh, we know what's happening, and that surely is what's happening. We wanted actually to test if, ordinary humans can use, essentially, can use these tools, can really get some intuitions about how the model works, and would these intuitions actually be causal as opposed to just, again, being some kind of confirmation bias or some other just cognitive kind of cognitive spurious, spurious effect. So, we did a bunch of experiments with MTurk. I invite you to look at the paper to look into them, but the answer is yes. Essentially, like we put quite a lot of work into trying to design the experiments the right way, and we did that. We think that the experiments are interesting. Also, just if you want to test some of your own solutions and just you would like to see if they work, but so they are of independent interest. But also, it seemed to like they seem to confirm that the primitives that we put forth, they really work the way as intended. So that we were happy about that. Okay, so. Yeah, so I told you about this whole like adversarial robustness, how it informed this like robust feature model, and like once you kind of realize, this like you think about this robust feature models, and you in particular view adversarial robustness as a prior and not just a property that you need from security point of view, a lot of very interesting and useful properties of the models emerge. Essentially, like the adversarial robust models, particularly in vision, seem to be really, really useful. Again, even if you don't care about adversaries. So. Is that all? Is this kind of this functionality, this ability to get better representation, is that all that we can take away from thinking about adversarial robustness in the computer vision kind of context? Well, and the answer is no. Okay, so essentially, it turns out that like once you have this this robust feature model in mind, then you realize that like both robust and non-robust features are useful, and essentially, again, adversarial robustness allows you to navigate between them. Okay, so if I look at about these two types of features that my datasets like have, then okay, so one thing that you can ask, okay, so essentially, so we know already that relying on robust features leads to kind of better representations, more human alignment representations, but you can then push it further. You can actually ask, okay, so what other downstream task can essentially benefit from the representations? And what we find in a recent paper is that actually the robustly trained model, they not only are easier for us to make sense of, they actually also transfer better on a variety of tasks. And that, by the way, might not have been obvious because I didn't talk about this, but like essentially there is a price that you seem to need to pay in terms of test accuracy. So average case test accuracy when you want your model to be, let's say, robust. So, and we know from previous work that like, the better test accuracy you have on the source task, the better in general you are on the transfer task. So, even though here robust models have lower test accuracy on the source task, they seem to still outperform, standard models on the downstream transfer task. So that was kind of quite interesting, and I invite you to look into the paper for more details. So this is kind of one takeaway from thinking about this robust feature models. But what was kind of the other realization that we had is also these non-robust features. Even if now you might think them as undesirable, they actually can be useful. In particular, we show how they can be useful to something we call data-driven object design, again, in the context of robust feature. So let's talk about that. So kind of, again, the point of start here is adversarial examples, okay? So this clearly is a problem if you think about having robust and reliable vision. But the question that actually we realized maybe you should be asking, okay, so as much as adversarial examples are a problem, maybe there is a way in which we can use adversarial perturbations that create these examples to be helpful for us, okay? So what's going on here? Well, essentially the question here is kind of about, changing the rules of the game a bit, okay? So if you think about it, is that in many scenarios, we have a fair degree of control over the objects we want to track or recognize. So you think about kind of designing a landing pad for a drone, about trying to track an object, a friendly object tracking. So imagine that this is a rescue boat and you actually would like to be able to track it reliably, and that's in everyone's interest to do so. Or if you think about wrong signs detection, it's like essentially we don't try to design our signs to make them difficult to spot, like we actually want them to be visible. So so we can have so we can navigate using them. So in all of these cases, you have control over how these objects are designed. And then the question is like, okay, so if you have control over how these objects look, can we modify or patch these objects by putting some patches on them to make them easier to robustly classify and to detect? Okay, so what do I mean by that? So this is kind of the concept that we call unadversarial examples. So the idea is that, okay, we know that standardly trained models, they are sensitive to non-robust features. And again, this can be used via adversarial examples to to mislead this model and kind of make them malfunction. But maybe the same sensitivity can be exploited to actually make them better at other tasks like tracking and classification. So kind of the analogy to have here is just going back to the road signs. Essentially, like if you think about the stop sign, well, it has this funny shape. It is red exactly to make it easier for humans to see it under a variety of conditions, even if there is snowing, even if this is rain, all of this was designed to make it easier for our visual perception system to track and detect. So how about we think of okay, as much as we design objects to be easier for humans to see, can we think of what would make an object, what kind of design of the object would make this object easier for machine learning models to see? Okay, so what kind of would be the analog of the stop sign? If we wanted the given neural network to be able to perceive it well across a variety of distribution shifts. So essentially think of fog, rain, some kind of other distortions and visual distortions. Okay, we don't talk about adversarial robustness here, although you could, but then you have to be careful with the threat model, because if you clearly can undo the whole design, then clearly you will not get anywhere. But kind of this is the mode we have. And once you kind of ask yourself this question, well, then you realize that there is quite a bit you can do. And it turns out that, indeed you can create this, undesirable examples. So here is just an example of a human design jet. And, yes, you can recognize it easily in a clean situation, but when there is a fog and dust, things might go dicey. So then you can think of an adversarial jet, which is kind of painted in this funny way that was derived essentially from the sensitivities of the model, driven by sensitivities of the model, in which this object becomes easier to see across a variety of situations. So essentially you are again adding this design that makes it easier for the model, not for the humans, to make the model easier to say. And then kind of you can look at across a number of different studies and different shifts. And you realize that indeed there is a lot of gain here. And by the way, this gain goes beyond just using the baselines like QR codes or something like some fixed designs that people use currently in robotics and get gains from this. What you are gaining here is much more. So this is kind of just things tested in just purely synthetic situations. Then we kind of took it to the next level and we look at simulations and figure out if there are this kind of gains there. But then we realize, okay, as much as simulations are nice, in the end, we want to see, okay, does it actually work in the real world? And that's what we did. So essentially, we actually took a bunch of physical objects, printed some unadversarial patches for them, and essentially and so how much better the detection of this kind of object is, and the answer is much better. And just here I just let me just play a video for you of kind of this is a garbage truck that again is actually gets largely misclassified by this state-of-the-art model, but once you put the adversarial patch, it kind of you get this robust fairly robust detection here. Okay, so again, this is still, there is much work to be done here, but hopefully it's kind of will inspire your imagination of what other things we could do here. Okay, so essentially this is all I have to tell you today. So let me just kind of try to summarize and provide some broader perspective on everything that happened. So first of all, I guess one fairly specific takeaway from that is that if we think about the phenomenon of adversarial examples, well, what we know by now that they arise from this so-called non-robust features in the data. And the important thing to realize here is that again, these features are they are strange to us, but they're actually legitimate features. They do help in generalization a lot, but essentially they make our models vulnerable to perturbations that manipulate them. Okay, so that's the first takeaway. This is kind of purely about adversarial robustness. If anyone asks you kind of what's going on with adversarial examples, essentially this is the high-level picture that you should have in mind. But then again, if you now care about better models, the important lesson implication from that is that if you make your models adversarially robust, what you actually end up making them is make them more human aligned, essentially make the representations be human aligned. And this is important because this enables a wide array of computer vision and debugging capabilities, as I just kind of demonstrated some of them in this talk. It also allows you to make this model more useful across many different tasks, because again, we tend to try to transfer models between tasks that we as humans could transfer to. So essentially, if the representations are more human aligned, they also seem to be more versatile when you kind of ask it to transfer from between such tasks. So in general, again, adversarial robustness might feel like it's a completely security-based concept, but the right way to me think about it is just as a framework for understanding what makes our models tick, how they learn, how they make decisions, and then kind of using this as an intervention, essentially once you understand that, you applying interventions to make these models better. And what better means depends. It might be just you just want to make them more robust to adversarial perturbations, but maybe you are after something else entirely, and and you still can use this kind of toolkit. And finally, I want to again highlight this new capability of adversarial examples. It's again, I really find it interesting and kind of stimulating. Again, in the end, it's a simple concept, but I think this kind of turning the tables on the adversarial robustness and kind of again using the sensitivity of models to non-robust features as a kind of as a plus, not a minus. I think there could be many more applications for that, and I think we can push this direction much further. So hopefully this will inspire also some of you to do that. Okay, that's all I have to say. If you want to read more about our work, essentially everything that I talked about in particular, you can look at our blog, and and I believe there will be a panel, and I will be happy to take questions there. Thank you.